Okay, today's lesson is lesson 34 for EE301. It also corresponds to lesson 39 for EE331. So let's go ahead and maximize our screen. And these are the lesson objectives. So today's lesson is on shipboard power distribution. So the big takeaway, if you remember anything from today's lesson, is that NSTM Chapter 300, that's Nav Ship's Technical Manual Chapter 300, that's Electric Plant General for the United States Navy. So all ship service operating procedures, operating instructions, steam and electric plant manuals, reactor plant manuals, all of them source this document for operation of the electric plant. This document is the source for ship service maintenance on electric plant, also safety precautions, safety procedures, and of course all your operating procedures, anything from pulling fuses to how to operate circuit breakers, of course working on energized gear. All of this is covered under NSTM Chapter 300, and this is the source NSTM for a whole series of electric plant nav ship's technical manuals. So it's just something to be aware of, to know where the right answer is NSTM Chapter 300. That's they call it the Electric Plant Bible for the fleet. So talking about ship service power. So all Navy ships, except for Virginia-class submarines, use three-phase 60 hertz AC. The AC is delivered at 4160 volts for the large ships, the aircraft carriers, the amphibs, and at 450 volts for ship service on all your smaller ships, submarines, destroyers, and cruisers. Power is supplied to the ship's AC distribution through the ship service generators. For the steam plants, we have ship service turbine generators. Those are steam-driven turbine generators. For the destroyers and the cruisers, they have gas turbine generator sets, or GTGSs. All ships have auxiliary ship service diesel generators as backup power supplies. Submarines actually have a main storage battery. And main storage battery, of course, supplies DC power, which is converted to AC through ship service motor generator sets or through static electronic reversible power supplies, or SERPOS units. And of course, shore power is your power supply when you are shut down and you are in port. So what does a ship service turbine generator look like? Well, this is actually a fairly very light picture. It's a small turbine generator. It's less smaller than what you'd see on a ship. It's the best representation that I could find that's not classified. A ship service turbine generator consists of a steam turbine. Steam turbine is going to have an inlet. The steam is going to drive the turbine. It's a rotary turbine that drives a shaft, which drives a synchronous generator. So the steam turbine is the prime mover. The amount of steam flowing through it controls the speed. Speed is controlled through the ship service turbine generator through the governor. The governor is a valve that regulates the speed by throttling the steam back in order to reduce the speed, or emitting more steam in order to increase the speed. And of course, the speed of the ship service turbine generator is going to be proportional to its frequency output. Since we maintain our electric plant at 60 hertz, we keep our turbine generators going at a constant speed, and they are controlled remotely at the electric plant control panels through a speed changer switch. Now, gas turbine plants use gas turbine generator sets. And gas turbine generator sets utilize compressed air on the rotor. So the rotor has this compressor on it, and this air intake. And it compresses the air, and then it emits the fuel oil, which is ignited with spark plugs, which produces the explosion in the engine, which of course the heat and pressure is what rotates the prime mover, which of course spins a generator. These units also have governors, which control the amount of fuel intake and the timing of the spark ignition, which controls the speed of the generator. And of course, the generator is going to be making a constant 60 hertz output. So the idea is to keep the speed constant and to vary the amount of fuel emission with response to the load on the generator. Diesel generators are used primarily as auxiliary generators, so they are backup power supplies. A submarine needs to, if its steam plant shuts down, if its reactor scrams, it needs to raise its snorkel mast or come to the surface and still raise its snorkel mast in order to emit air to supply this diesel generator. Diesel generators, of course, operate off the Otto cycle. And there's no spark plugs on the diesel generator, so don't be fooled by that when you go to your ship. But anyways, but the diesel generator is generally used as a backup power supply. And you'll notice that the infrastructure in actual physical size of a diesel engine is much larger than a steam turbine driving a ship service turbine generator. I found it surprising to me when I showed up to my boat, and our diesel generator on my submarine was rated for 850 kilowatts. But the engine that powers the diesel generator took up the entire length of the auxiliary machinery. Now, you can contrast that with the 3 megawatt ship service turbine generators we had in Ingram upper level. Comparatively, the steam turbine that is much more powerful, almost 4 times the power of this diesel generator. The steam turbine took up less than a quarter of the space, so it's very powerful for those steam turbines. But these diesel generators, like we said, are auxiliary generators. They're very reliable technology, and they're used to power your electric plant when your normal means is not available. Ship service submarines have main storage batteries for a DC distribution. So they have an AC distribution system and a DC distribution. The main storage battery, because it is a DC power supply, requires power conversion equipment in order for it to be useful to all of the ship's alternating current loads. The main sources of power conversion equipment for Los Angeles class, Seawolf class, and Ohio class submarines are either ship service motor generator sets, which have a cumulatively compounded DC motor on one end, and it's a motor generator, so it can be operated as both a DC motor or a DC generator, and a synchronous motor / synchronous generator on the other end. So it can convert power by discharging power from the battery to supply AC, or it can take AC power from shore power or from the ship service turbine generator, and it can be used to charge the battery through the ship service motor generators. SERPOS is a relatively newer technology, so it's static electronic reversible power supply. So it does the same job as a motor generator set, but it uses a big inverter and rectifier cabinet in order to accomplish it. The SERPOSs were first introduced at the S8G prototype up in Ballston Spa, New York, and have since made their way into the Ohio class engine. When a ship pulls into port, you want to shut down the plant. When you shut down, it means less watch standing requirements. People can go home to their families. So in order to shut the plant down, you still need to have electrical power. So we plug into the pier through the shore power joys. So we have the shore power joy connectors. Typically for a Los Angeles class submarine or an Ohio class submarine, they have 4 400 amp rated 3-phase cables, and very heavy cables. They have to be walked by the crew from the shore power pier substation across the shore power brow to either the forward or the aft escape trunk. So you can see in this picture, the crew is lowering the shore power joy into the trunk, and you'll have a person straddle the width of the trunk and then plug the joys into the 3-phase prongs within the shore power, within the aft escape trunk, which in turn plugs into is bus wired to one of the ship services switchboards. So with alternating current, so you have to, a lot of your power supplies, you got to be able to transfer power from one source to another. So if you want to shut down your ship service turbine generator, for instance, so your ship service turbine generator is up and running, it's supplying AC to your electric plant. Well, if you want to shut it down, you got to transfer the load from the ship service turbine generator to the new source. So if you're bringing the diesel online, or if you're bringing shore power online, you're going to have to parallel your generator with this new source and transfer this load. So the requirements for paralleling AC to AC sources are first that, well, you have to match the voltages. So the amplitudes, the RMS values of the voltages have to be matched from the incoming machine to the running machine. The next is that you need to establish conditions so that the frequency of the incoming machine is slightly higher than the running machine. Now, what does this mean? What does this look like? We use something called a synchroscope. Synchroscope is the center meter on this picture. The synchroscope compares the incoming machine's frequency to the running machine. So if your running machine was a ship service turbine generator and your incoming is shore power, it's monitoring both the shore power frequency and the ship service turbine generator frequency. So if the incoming machine is higher in frequency than the running machine, the synchroscope will spin in the fast direction. And likewise, if the running machine's frequency is higher than the incoming, it will spin in the slow direction. And this is important to notice because the incoming machine, in order to ensure that it picks up load at the moment of paralleling, needs to have a slightly higher frequency than the running machine. So the synchroscope spinning slowly in the fast direction, you would know that the AC sine waves of the two sources will be directly in phase, exactly in phase with one another when that synchroscope needle gets to the 12 o'clock position. That's when you know both the incoming and running are exactly in phase. Incoming might have a slightly higher frequency, but they are in phase right when that synchroscope is at 12 o'clock position. When they are in phase with one another and their amplitudes are matched, there's no difference in potential between the two sources, between your incoming and your running. So the idea is that you shut your circuit breaker in order to parallel the two sources right at the 12 o'clock position. That minimizes the transient on the electric plate. Just conversely, if that synchroscope needle was at, say, the 6 o'clock position, both sources would be exactly 180 degrees out of phase with one another. And that could be catastrophic for your electric plant because you would have, say, if you have two 450 volt RMS sources, they're exactly 180 degrees out of phase with one another. That means there's 900 volts of potential between the two across very, very low resistance of the buses, which could result in a very large current spike. So this is very important that your electricians get this right. Again, the synchroscope has to be right at the 12 o'clock position at the moment of parallel. So that's requirements. This particular picture looks like a 400 hertz motor generator set. So this looks like a picture of 1SF in the actual 1SF switchboard in a machinery room for an actual submarine. Okay, so what are switchboards? So I've been saying switchboards throughout this lesson. Well, switchboards are the point of connection for the generators of the ship and also the loads that they supply. So inside of a switchboard, it consists of the bus. When you hear the term the bus, we're talking about the very large conductors that carry the main current for the switchboards. We say it's the starboard AC buses. We're talking about the actual buses, the actual conductors that carry the current for the starboard half of the electric plant, for instance. Now, switchboards will contain circuit breakers and/or fuses, depending on the type of arrangement and the types of components that you have for your electric plant. And also any control and indicating equipment. So many of these circuit breakers could be remotely operated. So they'll have little dead front fuses on the outside, which will supply power to whatever servo is controlling the circuit breaker, whatever magnet is controlling the circuit breaker, and also to whatever remote control switch that is remotely actuating it. So you can see these particular switchboards also have meters for monitoring the loads and monitoring incoming sources, but the makeup and construction of your switchboard is ultimately going to be dependent on its purpose. Okay. So what else we've got here? So when you see the electric plant, you see the switchboards on the electric plant. They're going to be divided up as being either vital or non-vital. So vital switchboards supply vital loads, which are considered immediately critical to ship safety and control. Things like lighting, things like rudder control, things like all of your alarm and indicating circuits. So those are things that you need. Rod control, for instance, rod control on a nuclear-powered submarine. That is a vital load. The slow-speed power supplies for your reactor coal pumps, those are considered vital loads. So those are loads that you need to be able to drive the ship and see and be able to operate safely. non-vital loads, many non-vital loads are important loads, but you can live without them for a period of time. For instance, like a ship's R114s is the air conditioning plant. You have to have air conditioning plants to operate a steam room for any period, any kind of engine room, steam-driven engine room for any kind of a period of time. But you can live without it for short periods. So those are considered to be non-vital switchboards. Vital switchboards are generally arranged in schemes such that a backup power supply can take over. For instance, they'll be hooked up to an emergency diesel generator. So if the main generator goes away, the vital switchboard can be powered from an alternate source either immediately or very readily within a very short period of time. On submarines, you have the vital buses will be protected by the ship service motor generator set, so directly off of the battery. So if you lose the turbine generator that powers the starboard AC buses, for instance, a circuit breaker will open and protect the vital bus, isolate it from whatever the fault was because you lose the ship service turbine generator, and then the battery will then power the vital bus without interruption. So that's kind of the general scheme. Now you also notice in numbering, you can see vital switchboards are typically numbered with 1s and 2s. So you see like 1S, 2S, 1SA, 1SB, 2SA, 2SB. Any switchboards with 1s and 2s is the numbering. You know those are vital switchboards. So non-vital switchboards are just numbered greater than that. Typically, they start with anywhere from a 3 through a 6. I'm sure the larger ships may have may go up in higher number, but you'll see 5S, 5SA, 5SB, 5SC, etc. And it just kind of depends. The other thing to take away from this is that odd numbered switchboards are for starboard ship service components, starboard for power loads on the starboard side of the ship, and even numbered switchboards are for even numbered loads or for port loads and are considered port buses. So you have starboard buses and port buses. Even numbers are for port, odd numbers are for starboard. The S, of course, is for ship service, the naming schemes. Again, the A's and B's and C's could be, those are just sub switchboards to the ship service switchboard. For instance, a 2SA switchboard, for instance, is supplied from 2S. 2SB would be supplied from 2S. So you see these other, the other naming, the lettering schemes are just to differentiate a sub switchboard from a main switchboard. These would be battery switchboards, so you only see those on submarines. So you see 1B, 2B, 3B, 4B. There's no such thing as a vital bus on a battery. We don't really consider that. The whole battery DC distribution system is considered an emergency distribution system for submarines. Now, your surface ships will have the E designation in their radio schemes, and those are E-buses are powered from an emergency diesel generator, which kicks on upon the loss of the power supply, whatever the main power supply is. So those E designation means that these are switchboards that are fed from this emergency diesel generator. Okay. So the general schemes with electric plants are the radial, the zone, and ring bus. Ring bus is submarines for their distribution system. And then the type of distribution you have depends on the ship, its mission, and what its needs are for its power supplies, and also what its capabilities are. So this is an example of a radial distribution system. You can see the switchboards for the 1S and the 2S, the 3S and the 4S. We see this 1E and 2E designations here. And you see those emergency generators, which supply these switchboards, and it's not shown, but there would be bus tie circuit breakers, which would protect the vital components that are supplied from these switchboards, and also allow you to power non-vital ones also from it, but with preference for the vital is how it would be arranged. So your electric plant lineups is something you're going to run across when you come to these ships, electric plant lineups. Electric plant lineups are determined by the circuit breaker open-close arrangement. So, for instance, you may want to have a split plant electric plant lineup. So a circuit breaker, a bus tie breaker between the 3S and the 4S, for instance, will be open. So that way a fault on the 4S switchboard or some kind of a short occurring here on the port side will not affect the starboard. So that way it allows for fault isolation and fault separation. So that's what they mean by split plan operation, where your port buses and your starboard buses are separated from one another or opened by a circuit breaker. Now you could argue that you lose perhaps reliability of having two power supplies feeding it in parallel, but at the same time, you increase reliability through fault separation. So what else? We got, so for circuit breaker functions. So these are the general functions of circuit breakers. Okay, so supply breakers. Supply breakers would be things like your diesel generator or your ship service turbine generator output circuit breaker. So think of the turbine generator as being the power supply for the buses. So its output breaker would be called a supply breaker. You have what are called bus tie breakers. Bus tie breakers they tie two different buses together. So if you want to tie your starboard buses to your port buses, you will have a bus tie breaker which separates them and allows you to parallel them or to operate split plans. So you can have it open or shut with the circuit breaker position depending on your desired mode of operation. Feeder breakers are breakers on switchboards that supply lower switchboards. So for instance, you may have a circuit breaker on switchboard 2S, which feeds switchboard 2SA. So the smaller switchboard is fed from the bigger switchboard. Then of course you have individual load circuit breakers, which isolate individual loads. So you'll have a circuit breaker that supplies the slow speed power supply windings for your reactor coolant pumps, for instance. And so that would be an example of a load circuit breaker. Now, electric plants also employ a scheme called selective tripping for overcurrent protection. What is this selective tripping? What does that mean? Selective tripping means that it's the selection of overcurrent trip characteristics such that the circuit breaker or fuse that is nearest the fault will trip first. And this minimizes the effect on the rest of the electrical distribution system. So looking at this picture here, so we'd see this perhaps these lower loads 5 through 7 could be some lower switchboard here supplied by a 100 amp circuit breaker. Well, if a short were to occur in load 7, we would want just the circuit breaker supplying load 7 to trip. We wouldn't want to lose power to the whole panel and interrupt power to loads 5 and 6 just because one load had some kind of a fault condition occurring to it. Also, if the whole bus shorts out, we would want its feeder breaker to trip and not lose power to the other panels and affect the rest of the distribution system. So again, you want the circuit breaker or fuse that is nearest the fault to fail or to trip open. That way it minimizes the effect, the interruption, and prevents interruption of power to the rest of the electric line. And you'll see this on your ships. Other things that you'll see throughout your ships are what are called P panels. And P panels are they're just small mini switchboards, if you will, that supply collections of loads that are either similar in function or they're in close proximity to them. For instance, like LR5 is an example of a P panel on the submarine, which supplies only the nucleonics loads. So just all of the loads of nucleonics, which is for the engineering laboratory technicians, that is supplied off of just one panel, and so just by approximation, so if there's any kind of an interruption of power for any of their tests that they're doing, they know exactly which panel to go to for that. And these panels can be of either fuse types. So the one on the left, you open the cover to the panel, you'd have access to the fuse holders. And those kind of fuse holders, there's some special requirements to be able to pull those fuses, obviously, because it's energized buses behind those fuses. Tag out user's manual will require you to actually tag out the power supply. So if there's a circuit breaker that feeds this P panel, you'll have to open that circuit breaker, hang a danger tag on that circuit breaker before you can go into it to pull the fuse. So just be aware that can be a requirement for your ship. Now, some loads can be powered by two or more different buses. This is achieved by use of what are called bus transfer switches, which can be either automatic or manual. So ABTs or MBTs is what we call them. Automatic bus transfer switches have a spring mechanism and a sensing coil. So upon an interruption of power, the ABT will then trip the spring, and the spring will immediately, in a very, very small fraction of a second, move the contact from the primary power supply, which we could say is the #1 switchboard in this picture, over to the #2 power supply. It would do it automatically, so without any, it will not require any operator action. The ABTs will have an option for either manual or automatic reset. So upon restoration of power, there will be some kind of a time sensing relay that will sense that the power has been in place for 30 seconds or whatever the timing requirement is. Then after 30 seconds of restoration of the primary power supply, the ABT will automatically transfer back to its normal power supply. And then, again, this depends on the types of loads. There's a lot of maintenance that goes with these ABTs, and requires these special photo tach instruments to be able to verify their timing, and their switching as fast as they're supposed to, and also we'll monitor the output of the power supplies to verify that it's not going to be adverse to the load for the interruption for the switch off. So again, ABTs transfer this power automatically, and NBTs require you to manually ship it. So a lot of your P panels, for instance, may have NBTs on them. Most of your P panels will be supplying non-vital loads, which you might want to. It might be good to have. Maybe something that if you've got, for instance, your starboard AC buses are going to be down for maintenance for some period of time, you can switch all your starboard powered P panels over to their port power supply manually, so that way you're not without those loads while the buses are down. Now on ships, we have 120 volts distribution systems also. Specifically, the ship service distribution is, like we said earlier, is either 4160 or 450 volts, depending on your platform. But you still need to have 120 volts for outlet and lighting loads, okay? Because the ships are obviously American ships, so they use American lighting systems and American receptacle outlet systems. So they have to have 120 volts. And these are stepped down through, you'll see these little transformer banks like this one throughout the ship, wherever you have networks of 120 volt loads. Now, one critical difference between outlets on ships and outlets in residential, commercial, land-based facilities is that the ship it operates on an ungrounded system. It's an ungrounded system. So what does that mean for an outlet? Well, in your home, you have what's called a hot lead. So that's the energized conductors. That's what's connected to the energized bus in your house. Then the load is wired through the plug. The plug you may have some kind of an on-off switch on your load. So think of it like a vacuum cleaner. You plug into your outlet. The plugs form the connection. Then the power goes through the hot lead, then through the switch on the vacuum cleaner, through the motor on the vacuum cleaner, and whatever lights or anything else fancy that you have on it. Then it goes to the neutral. The neutral is, of course, grounded in North American distribution systems. Now, on a ship, though, the neutral plug is not grounded. It's not grounded. So what does this mean? This means that 120 volts, it still has 120 volts potential between the two plugs, except for now on ships, it's actually an across the line voltage instead of what we call for a home distribution. It would be a phase to neutral voltage. So this would be phase to neutral. Well, on a ship, it's across. You get 120 volts root mean square across the line. So think of it as a two-phase. It's a two-phase distribution with 120 volts across the line. And there are some power supplies that do have trouble with this. I remember we had when I was on the Albuquerque back in 2003, we had these Toshiba laptops. Toshiba makes is a Japanese company, obviously, and they were making laptops. But their power supplies, there was some little quirk to the power supply for the computer where the neutral and the ground were connected somehow before the rectifier in this thing. So as a result, when we plug in the ship's power supply plug in these laptops to the ship's power supply, they were actually causing a shock hazard because this lead that was not expected to be energized by Toshiba, because they expected you to be plugging it into your home outlets, was now suddenly energized. And there's a path, and it would actually energize parts of the case of the laptop, and the officers that were using it, because I was enlisted at the time, but the officers in my boat that were using these laptops were actually getting shocked when they would plug these laptops in. So just be advised, some power supplies may not like this, and may not be compatible with it. And your ship's electrician should have a list of equipment that is known not to be compatible with the ship service distribution. You should be checking with your electricians before you plug anything on your ships. Electricians also do general electrical safety checks on your equipment to ensure that there's no paths to ground to the case on your equipment. They'll do mega resistance checks on it to ensure that that is the case, that there's nothing on your equipment is shorted to the case, so before you plug it into a ship's distribution system. Now, ungrounded systems. Now, why do ships use ungrounded systems? The answer, in short, is that they are considered to be more reliable than grounded systems. Specifically, in an ungrounded system, you could have a short, say you have some flooding condition, for instance, and one of your phases were to ground out on your ship in one location. Say one switchboard got grounded out, or one load got grounded out. You still would have a path for current to flow between the phases in this ungrounded distribution, so there'd be no interruption of power in this case. It would actually take multiple faults. In an ungrounded system, it actually takes multiple faults, second grounds, third grounds, and so forth. And they'd have to be pretty hard grounds in order to cause an interruption in power. So the idea is that if you get a really hard short on one portion and a second very hard short, you could potentially have a path for current to flow through the ship's hull, through the ground path. But again, it takes multiple shorts in order to interrupt power for an ungrounded system, whereas a single grounded system, it would cause an interruption of power right away. So again, they're considered to be more reliable. But with that said, it is a misnomer for some people that if your distribution system is truly ungrounded, that would mean at no point is there a difference in potential between your conductors and your ground. There's no path for current to flow because the ground is not part of the circuit. But that's actually a misnomer, because in reality, there's no such thing as a perfectly ungrounded system. There's always going to be little paths to ground. In this case, we can see on this bottom right picture, we can see that the resistance is not infinite. It's some value, it's some high value. It could be 5 mega ohms, for instance. But there's still some path for current to flow to ground. And of course, anytime there's a conductor and there's an insulation, there's two conductors and there's insulation between the two, there's going to be some capacitance also between the conductors and the ground. So there is a path for current flow, and your ground, for intents and purposes, is neutral even to an ungrounded system. So yes, you will get shocked if you touch an energized conductor, even on a shipboard system. And because of the concern about the effects that inadvertent grounding on our electrical distribution, any interruptions of power and the problems it can cause, and also shock hazards that it can cause, we do a lot of ground detection monitoring. The two general types of detectors are active ground detectors, which employ an active voltage signal, which you generally only see these on electric plant control panels, but you'll see them there. And you're applying an active source, measuring the return current in order to be able to measure it. This is a very accurate way to get the current grounds on energized buses. Now, passive ground detectors take advantage of the fact that there is always some resistance, some very high resistance, and some capacitance effect from each phase to the ground. So if one phase is more grounded than another phase, what's going to happen is that we'll introduce a path for current to flow in a lighting circuit that you see here on the right. The idea is that this grounded phase would then be a path would be causing current to flow through that. So it would cause the other two lights to they would brighten with respect to the phase. So my cursor is over this this middle phase here. So if this is more grounded, there's more of a path for current to flow through this. So there'll be more current going through this winding here, this light, which is represented as a winding here, than the other two. So this will appear dimmer, and the other two will appear brighter in the case. So again, this would be a case where the Bravo phase has some kind of a ground, some kind of a short on it, or some kind of a short path to ground on it. You see these lights would get brighter, this light would get dimmer. And the same would be for the other two phases. So if one phase is grounded, more grounded with respect to the other one. This doesn't give you an actual quantifiable measurement. So again, this is just typically you'll see, you may see some kind of a guidance on the panel which says if it appears this bright or this dim rather, it could be indicative of a short of less than 5 megohms, for instance. But you have to actually measure it and actually tag out the switchboard in order to get an actual measurement. This is more of a quantify. This doesn't really quantify it. This is more of just qualitative. Hey, it looks like we got a short on our Bravo phase. So that's what a passive ground detector does. Now, the other thing and last thing we're going to talk about is another important concept. This concept is called the concept of grounding straps. Specifically, we're showing a load here. So this is a load, this is a motor, and the little stick figure is touching the case of this motor. We see this, it's called resistor R3 here. This is just representing that there may be some path from this motor winding between Echo and Charlie terminals here. There could be some path for current to flow from this winding to this case. Well, if, say this got submerged or there's some kind of a short occurred between the windings and the case, and this resistance was very, very low. Well, generally speaking, if there is a grounding strap, this grounding strap provides a short path from this case to the ship's hull. The idea is that there may not be, there's definitely not enough power in this circuit in order to be able to energize the ship's hull. But if I were to take this grounding strap out, right? If I took this grounding strap out, there could possibly be enough energy in the circuit to be able to energize just the atoms in this case, just to bring those atoms in the case of the component up to conduction band. But there's never enough energy to energize the hull. So the whole idea is that it provides a positive electrical path from the metal cases of ship's components to the ship's hull, so that way, even if they are shorted, there's no way they could become a shock hazard to people. Okay, well that completes my lesson today. You're welcome to contact me if you have any questions on it.